Recently, Evident released software version 5.12 for the OmniScan X3, which added several new features to the system. The one that I'm most happy to see is the Wedge Profiler, which is an automated way to verify your wedge angle and measure the height of your elements, namely H1, the height of the first element. When performed correctly, this eliminates the need to do an old school wedge delay calibration, as well as a traditional wedge angle or refracted angle verification. The process will provide the most accurate wedge information to the focal law calculator, which is crucial for proper focal law creation and precision of your time of flight measurements. It works great for flat wedges, as well as those pesky COD and AOD wedges, which are historically difficult to calibrate since they don't sit very well on a calibration block. Also, the process works equally well for phased array and TFM, but it's not a new process. Some of us more seasoned phased array techs may recognize this as an acoustic wedge verification, which is something that we've been performing manually for over a decade now, and I've been teaching it for several years as well. It's also been on board other instruments and other software platforms for a while now, so I'm happy to finally have it as a software feature on the OmniScan. In this video, I'll walk you through the old school manual process first, and you'll see that it can be very time consuming. So then I'll probably have to do a second video and show you how it works on the OmniScan with the new software feature. And I'll try to show you how to get the most precision out of each version. So stay tuned and let's level up those UT skills. As we all know from our phased array classroom training, the focal law calculator that's within whatever software you're using has to be informed of several different wedge parameters in order to effectively do its job. The three most important wedge parameters to get right are right here. So number one, wedge velocity. Number two, wedge angle. And number three, height of the first element. There are other wedge parameters that are also important, but these three are at the top of the list. If any of these are incorrect, we will have bad results, guaranteed. If multiple parameters are incorrect, then we're really asking for trouble. So these inputs need to be as accurate as possible. With phased array, the standard material that we use is something called Rexolite. It's a cross-linked polystyrene, and I've got some of the velocities right here on the screen. For today's discussion, let's just assume that our wedge velocity is a constant. So the next parameter we're interested in would be wedge angle, which along with velocity would directly impact our refracted angles. So again, think about Snell's law. From the factory, all wedges will have slight machining tolerances for all relevant dimensions, including the angle. So that means that even brand new wedges could vary slightly from nominal measurements, not to mention what happens when we wear these wedges out during use. Remember, wedges are consumable items, expensive consumables, but consumables nonetheless. The only difference between this wedge and this rag is a few $100. They're both intended to be used up and discarded eventually. But the wedge profiler, by using it is possible to extend the life of your wedges when they wear out to an extent, of course. Historically, to verify wedge angles, we would want to place our probe on a calibration block, kind of like the IIW here. This works for conventional UT as well as phased array. So step one, find the beam index point. Step two, verify the refracted angle. Typically, our wedges are said to be in tolerance if our refracted angles are within plus or minus 2 degrees of nominal. If you're watching this video, I assume you already know how this works. If not, I teach it in my UT Level 2 and my phased array classes. So come see me if you need that basic training. I can tell you from experience that this gets skipped all the time. So there's a lot of reasons. We get lazy. We get rushed by management and clients who have no clue what's required for us to do our jobs correctly. Sometimes we get poorly trained. Sometimes maybe we just don't care. This process is a time-consuming one with phased array, but it is very important. Problem here, it does not work for curved wedges. Usually we've got to use those for code compliance on smaller diameter components, but I can't put a curved wedge on a flat cow block. So what if I told you there was an easier, quicker way that works with curved wedges and flat wedges? We're getting there. The next major wedge parameter for us to consider will be H1, the height of the first element. If the focal law calculator knows the precise probe parameters and the wedge angle is known and the position of the first element is known, it can then calculate the position for all the other elements and then properly do its job. But just like the wedge angle, there can be error due to machining tolerances and even worse, wedge wear. That's where our familiar wedge delay calibration comes into play. So it's designed to measure and offset the wedge paths for each focal law with phased array, ensuring that acoustic zero, meaning, where the sound exits your wedge and enters your part, is consistent across the entire wedge surface, regardless of the properties of each individual focal law. It's effectively the same process as a delay or your zero offset function with conventional UT, with the exception that it's performed for each focal law. When you perform the traditional wedge delay calibration, it's assumed that the wedge angle is already accounted for. All that the traditional wedge delay calibration can do is adjust the wedge height by calculating H1, height of the first element. It will not correct for any wedge angle error, whether that's due to wear or machining tolerances or any other source of error. It can only account for level, even wedge wear, which actually, that's hard to do in practice. Typically, our wedges are not worn evenly. They're typically worn at an angle, so this angled wedge wear can have a major negative impact on our results. If your wedge has excessive front wear, it means your refracted angles are going to be lower than nominal. And if the wear is towards the back, the refracted angles are going to be higher than nominal. And again, the traditional wedge delay has no way of fixing this. Also, the traditional wedge delay does not work with total focusing method, and the reason is there's no focal loss for us to calibrate with TFM. So what can we do about it? This is where the acoustic wedge verification comes into play. Back in 2012, Olympus, now Evident, they were putting out webinars and videos regarding phased array on a regular basis. So I used to just sit back for hours and watch these videos and learn all sorts of cool tricks and knowledge that you really just can't squeeze into an 80-hour phased array class. Most of the things I've learned about phased array came after my initial training, not during. There's a wealth of information in these videos, and I'd recommend to any current or aspiring phased array tech to just sit back and binge these videos just like you would your favorite series on Netflix. One video in particular was super informative, and it was called Understanding Phased Array Time of Flight Calibrations for Improved Sizing. This was presented by Chris Magruder, and I'd recommend you watch it from start to finish. It is a pretty long video, so they were all about an hour long, give or take, at this point in time, about 10 years ago. So on this video, at 39 minutes and 51 seconds, the acoustic wedge verification is presented. After watching it a few times and learning the process, I checked several of the wedges that were being used by my group on a regular basis, and I was shocked at how far out of tolerance some of these wedges actually were. So I'll walk you through the process a few times. We'll check out a few wedges, and I'll also show you some extreme examples that I've encountered over the years. Okay, before we jump into the acoustic wedge verification, I want to go over a couple of basic things, show you some signal characteristics on my OmniScan here. So I've got a 5L64A2 transducer, and I'm running contact without a wedge on this 1-inch thick carbon steel PAX block. And I've got a nice back wall signal there. So I'm going to pause the instrument real quick, and I'm just going to kind of show you some of my settings. So I've got a range of about 1.5 inches. So here's my 1-inch thick back wall. I ran a really high points quantity in order to get no compression. That way I've got the full resolution of this A-scan waveform. And I've got a video filter off. So what I can do, and I'm just going to look at just my A-scan only, right? So I'm going to zoom in. And by zooming in, and since I'm running this really high points quantity, low compression, I can see all the individual lobes of my A-scan here, right? And these are going to be all my positive and negative displacements from my RF waveform, but I'm looking at a rectified signal right now. And also, I've got some gates set on my signal. So gate A, that's the red gate. I've got it set to read max peak, and we've got a thickness reading over here, or a sound path reading. And so there's no wedge delay. I haven't done any calibration. This is just plug the probe in, make a setup, put it on a cal block, see what happens. So the highest peak is reading right here, and that's going to be, oh man, I went way too far. This is going to be where I get that 1.044 reading right here at the max peak. Gate A is set to read max peak. but I also placed gate B in, pretty much the same spot. I separated them a little bit so you could see the difference. But if I look at gate B, the green one, you can see that I've got it set up to read edge. So I've got a gate A max peak reading, and I've got a gate B edge sound path reading. And obviously they're giving me slightly different information. So the max peak is here, 1.044. But the edge that gate B is seeing, it's right here at 1.029. So the edge of the signal versus the max peak. So just like conventional UT, obviously we use different gate strategies for different things. So often if you're doing maybe a corrosion exam, maybe you run an edge gate or even a first peak gate, and you monitor this leading edge of the signal. So that's what edge would be really good for. Oftentimes in your automated and your angle beam testing, we use max peak. So max peak, and that's also the default measurement mode in the OmniScan. So they've all got their pluses and minuses, right? Max peak is more stable when you have amplitude fluctuations. As you can see here, I'm just kind of turning the gain up and down, and you can see that my max peak reading is staying consistent. But this edge reading, this is going to kind of change a little bit, just kind of based on what edge is actually being picked up, right? So as the gain goes up and down, now the edge reading is going to hop over to this first lobe because I turned the gain up, right? So 1.018 is right there. I had an edge shift left and my measurement got smaller, but notice that the peak measurement hasn't changed. If I turn the gain down, what's going to happen is edge is going to have a shift to the right, which means it's going to measure thicker. Right now it's reading 1.028, which is like right there. And the more I turn the gain down, you'll see that these edges are going to jump around. Now it's going to hop over to 1.044, which is right there. So the max peak gave me a more consistent sound path measurement when I had amplitude fluctuations, which we'll often have when we're doing automated scanning. But the edge gate, it changed as my gain went up and down. And then the same thing would happen if we were using first peak. So, and again, each one of these gating strategies has its up and its down. If I'm doing thickness testing or even manual, just any kind of manual UT where I can adjust the gain up and down on the fly, I'll often use an edge gate. But when I'm recording data, especially on instruments that don't have a lot of soft gain, the OmniScan X3 has almost an unlimited amount of soft gain, so you can do a lot with it. But on older instruments, we didn't. So max peak was the default. Now I've changed gate B to read first peak. And so it's reading the first peak that's crossing the gate. So right now there's my 1.033. But if I turn the gain up, now this is going to become the first peak, right? So again, you usually get more precision when you measure to the first peak or even to an edge. But if you have amplitude fluctuations, you're going to get edge shifts to the left and the right. And so, more precision maybe with first peak or edge, more consistency with max peak. And so that's a little bit about these gate settings. I'm going to focus here on gate A more than anything. So in addition to the gating strategies, right? If I wanted my measurements to read correctly, I'm going to have to do a wedge delay calibration or something. And we're familiar with that with phased array and conventional UT. So let's say that, I'm going to start off with this gate. I'm actually going to have it in first peak because I want the first signal that crosses the screen. I'm just going to pin this over here. Let's say that I want the first peak, and I'm going to crank the gain up to where this first lobe is the first peak. Let's say that I really want to dial this in so that the first peak measures my proper 1-inch thickness. If I did a wedge delay cal, it's essentially going to do the same thing that a conventional wedge delay would. It's going to add delay in order to get this thing to measure correctly. So as you can see, I'm adding delay in microseconds here. I'm doing this manually. Typically with phased array, you would do this with a calibration, but I just want to show you, what's happening. It's manually adding in delay, just like conventional UT. And I'm going to dial it in until this measurement lines up correctly. So almost there. We're going to say right there. Okay. So I needed 0.19 microseconds in order to get my first peak measurement to be correct. Okay. Well, now let's say that I was running at a slightly lower gain level. And hell, just for the hell of it, I'll turn on a video filter. And let's say that instead of first peak, let's say I was using an edge measurement. So I'll just change that, all right? So let's just change this to edge. Okay. How much wedge delay would I need to add in to get this to line up? Well, a little bit more. So 0.19. I'm going to dial in a little bit more. Okay, to get edge, I needed 0.2 microseconds. And again, that's amplitude dependent, right? If I drop my amplitude, well, I need more wedge delay added in order to get that edge measurement to line up. Okay, so, you know, we're talking about 0.2, 0.26. It depends on my gain. Well, what if I wanted my peak measurement to line up? So I'm going to change gate A back to max peak. And then we're going to hop back to UT settings, and let's see how much wedge delay I would need in order to get this to line up. Obviously, a little bit more. So with conventional UT and conventional phased array, before you do any wedge calibrations, like a wedge delay or a zero offset or any of that sort of stuff, you typically are going to set your gate detection strat. Look at this. I needed 0.4 microseconds to get this thing to dial in right. So before you do any wedge delay calibrations, you're going to want to set the gate mode to match the way that you're going to use it during your testing, right? If you're going to use peak for your examination, you need to get that set before you do your wedge delay cal. If you're going to use edge or first peak, you need to set that before you do your wedge delay cal. And I'm talking about a traditional wedge delay cal. And what we're going to see is the same thing's going to come into play when we do this acoustic wedge verification. You want to set the gate to the measurement mode that you're going to use for your test. And I'll show you how that works. Just one second. Okay, so now what I've done, I've added a 0 degree wedge to my 5L64. And we're going to look at the back wall signal that we would get here on this 1-inch thick cal block. And what we're going to do is kind of look at the same measurements that we looked at before with the contact. So I'm just going to hop into just an A scan, so we can really see what's going on here with my signal. And I'm going to zoom in again. So as you can see, I've got gate A set to read max peak. And so the maximum peak measurement that it's getting, and again, I've got a wedge on here now, right? This is no longer contact. So that's my 1.042, my max peak reading. I've also set up gate B just to give me an edge reading, and I've got it down pretty low where it's catching on this first lobe, right? So you can see it's reading 1.03. So if I just take this cursor and put it right about there, right, the edge of this signal, that's where this gate's reading. And if I brought the detection threshold up of this gate, then, you know, it's going to read this edge now, 1.014, right? So the gate detection threshold really matters here. Okay, so what we're going to do now, I'm going to show you the acoustic wedge verification. So I've cleaned off any couplant from the bottom of my wedge. I'm going to be using the back surface of the wedge as a reflecting surface. And I'm just going to set that down on the table. And I started a new setup, and I'm just going to walk you through the process of making this. So on the OmniScan tab 1, this is where we identify our part. This is one of the few times where none of this matters on this page. I'm going to go to tab 2, and I'm going to pick my transducer. So we're going to use the A2 transducer, 5L64, and I'm going to keep the wedge on contact because I'm going to be measuring the wedge. And then I'm going to go to tab 3, groups. And you can either pick a linear or you can pick a 0 degree with overlap. It doesn't matter. L wave matters. Element quantity of 1 matters. And focusing doesn't matter. You can't focus with one element anyway, so none of this is even relevant. So I'm making kind of like if we're doing an element check, right? I'm firing every element individually from this 0 degree wedge. And what it's going to give me is a wedge back wall signal down here that I'll be able to take some measurements on. So I'm going to make a couple little changes here. Make sure that my range looks pretty good. I need to change the velocity. So we're using Rexolite. The velocity of Rexolite is about 0.092 inches per microsecond. So I'm going to physically change that here on the UT settings screen. And you'll see when I do that, it actually changes my range now that I've introduced a new velocity. So I'm going to put that range back out where I can see the back wall a little bit better. And let's see, we'll go through. I'm going to bring my voltage down because sometimes I find this really powerful pulsar might be a little too much for this. I'm going to go through, and so I like to set a really high points quantity to eliminate my compression as much as possible. So I'm just kind of bumping this points quantity up to like 2,000 or, some high level. I'm actually doing a video on points quantity pretty soon and compression and net digitizing frequency. I'm not going to explain that too much right now. That one will be coming out pretty soon. I'm going to turn off gate I. That's this yellow one, and it's just kind of in my way. It bothers me if I'm not using it. And I'm going to put the gate over here on the back wall. Okay. And I'm just going to kind of auto 80 my signal. So by default, I'm in a max peak mode, meaning the measurement that it's taking right now is right there in that maximum peak, right? So that's where that 802 is coming from. But imagine if I was in an edge mode. Okay, well look, now it's measuring 793. So that would be over there at the edge of this gate, right around there. And if I was in first peak, maybe that would show up as well. I'd have to turn the gain up to really see it and probably turn off this video filter. So let's just see if we can see what first peak would show. Bear with me real quick. Got that. Let's just look at just an A scan just to kind of point this stuff out. And I'm going to zoom in down to this area on the A scan, right? So if I were to turn this to first peak, then the number that it gives me will actually be a little bit different as well, right? So 801 is max peak, 792 is edge. First peak, I'm getting 793, so kind of close to the same signal right here. Am I reading the edge or am I reading the first peak? Man, it depends on your gate. You've got to set your gate before you do this. So let's just say that that I plan on using max peak for my exam. I'm going to set this to max peak, and I'm going to take a measurement. So TA, that's going to be the measurement of the back wall, and I'm getting a 0.801. And what I usually will do, that's only on VPA1, right? So I just kind of scroll it out amongst the VPAs, and about 801 or 802 is a pretty consistent measurement all the way across. I think 802 is a little bit more consistent, to be honest with you. So yeah, I would go with 802. That's a pretty average depth across this entire thing. So I've acoustically measured at the velocity of Rexolite the peak measurement of this wedge. So what I'm going to do is this. I'm going to go down to my probe and wedge manager, and I'm going to adjust a factory wedge. So I know this is a kind of a slow process. I'm going to adjust this factory wedge. So, and we're going to rename this. I'm going to put dash PK for peak, and then I'm going to put today's date. Today was 1/31/23. That way I know what wedge I've got, right? So 1/31/23. I'm keeping the velocity and the wedge angle the same. What I'm going to make a change is right here. So by the factory default first element height or thickness of this 0 degree wedge was 787 inches, but I measured 0.802. So I'm going to put this in 0.802. 0.802. I've got to make a change. Sorry. I've got to tell it both of these numbers, 0.802 for the height and 0.802. See, there are a lot of steps here. You got to make sure you get all these things right. It sure would be great if we had a software version of this, right? So those are the only two changes I've made. So I'm going to save those changes. And I've now made a custom wedge. I'm going to hit done. And what I'm going to do is go back into my setup that I was running a minute ago where I was measuring the back wall. So that was my 5L64 0 degree setup. Going to open that one. And that's the one that we were using on this 1 inch thickness a few minutes ago. Okay, so again, I want to remember that, bring this gain down so I can find the back wall. The peak with the factory default wedge was giving me 1.042. Edge and first peak were getting me a lot closer to the measurement here, around 1 inch. Watch what happens when I choose that custom wedge. And remember, we measured it with peak. So if I go through here, and instead of that one, I'm going to pick the one that I made earlier, which is down here. Yep, I'm going to select that. And remember, the height of the first element, the measurement was slightly different than the factory version. The reason it was is because I measured it with peak, which is the mode that I decided that I was going to use for my test. And look at that, right? Now my peak measurement is much closer than what it was before. It was 1.042 earlier. Now it's reading 1.0004, which is pretty close. We're talking about 1/10 of a millimeter here, right? I could further dial this in if I wanted to, but I'm not going to bother. I would say that's plenty good enough. Look what it did though. Look at that edge reading. When it corrected my peak reading, now the edge reading is like way off because I delayed everything in order to get the peak to the right spot. So that means that I'm, half quarter wavelength off over here, depending on whatever lobe the edge reading is tripping on. So you want to make sure that you do this acoustic wedge verification in the gate mode that you're going to use. Let's go back and do it one more time. And I'm going to do it in edge mode. I should have saved the setup, but I didn't. So, we're doing this live here. I'm going to go back. And I'm going to do an acoustic wedge verification, but I'm going to set my gate mode to edge. So 5L64. Contact. I'm going to clean the coupling off my wedge and just put it on the table like I did earlier. Got to change the velocity under UT settings to the Rexolite velocity. And I'm kind of rounding it to 0.092. It's close enough. So when that happens, you will see a shift in your screen range. So I need to kind of tighten it back up a little bit. I introduce a different velocity. That'll be good enough. And then also what I want to do is I'm going to run a high points quantity, something that gives me, very little compression. Yeah, that's good enough. And I'm going to adjust the gates real quick. And going to get rid of gate I. That interface gate, if you're not using it, it's in the way. So I'm just going to move it out. Put the back wall over here. And I'm going to change this detection threshold from, I'm just going to change it to edge instead of peak. Okay, and I've got my overall signal at 80%. So looking here at the sound path or the thickness measurement of the wedge, since I'm reading edge, remember peak was 802, edge is reading 793. So I'll just kind of go across my VPAs and you see how that's remaining consistent. Also my gain's remaining consistent. If the amplitude of the signal was going really up and down a lot, then I wouldn't have any consistency. But in this case I do, 793. Okay, so what I'm going to do, just like I did earlier, I'm going to make a custom wedge, but this time it's with those edge measurements. So new from, I'm going to go down and pick the factory default wedge, and 790. You know what? I've already forgotten. That's 793. So we're going to do 793 for this, for that. I'm going to rename this one edge, today's date. Save it, done. Going to go back and open my 0 degree setup. Put it back on the cow block to get a nice back wall signal. And I'm going to go through and I'm going to select that edge wedge that we're using now. So probes and wedges, instead of the factory, I'm going to pick user, edge, select, done. And I'm going to go through and change gate A from peak to edge. And look at that, right? B was already on edge, but look, I had it really, really low. It was down there on that first peak. A, same amplitude. By doing the acoustic wedge verification in the gate mode that you're going to use for testing, you're going to get more accuracy. So just like a wedge delay cal where we're adjusting the height of the elements, we're adjusting the wedge delay based on the gate detection strategy you're going to use for testing. When you do the acoustic wedge verification, you got to do the same thing, right? Peak will have a little bit more delay. Edge or first peak won't have quite as much delay. I think naturally on the OmniScan, honestly, the first peak is usually the where it wants to read at to begin with natively. The first peak usually lines up closer to the nominal position on the screen, and then we have to calibrate one way or another to make edge or peak line up correctly. So that's how you do an acoustic wedge verification on a 0 degree wedge. Super easy. Next, I'll show you how to do it with an angle beam wedge. Okay, so now I've got a 5L16 mounted to a N60 60 degree shear wave wedge, and we're going to kind of look at a few of the same things that we did with the 0 degree, and then I'll walk you through the acoustic wedge verification and we'll check our results. So first things first, I'm going to get on this 1 inch radius on this PAX block, and what I'm looking for is right there. So I'm peaking up the signal from this 1 inch radius. And again, I have no wedge delay calibration. I haven't modified the wedge parameters or any of that sort of stuff. So I'm just looking at the signal, just the way that it's natural, right? No adjustments to any delays. I'm going to bring the gain down just a hair so I can really find that peak. And, we'll say it's about right there. Okay. So sound path. I'm using a 1 inch radius. So the sound path reading, if it was ideal, it would read 1 inch, right? But I'm going to have to make a correction. So typically you would just do a wedge delay on this radius and then everything would line up right. Well, let's look at the acoustic wedge verification version. But before I go there, let's just see how close. So I'm going to put the signal at 80%. And then we're going to see what the other modes would have told me. So peak is reading 1.035. And I've actually got my gate starting at 1 inch right here, so we can actually see where the instrument thinks that 1 inch ought to be. And you can see that it's a little bit before my signal. And I'm going to zoom in again. Okay. So if I were to change this to edge, then boom, look at that. SA is measuring 1.09. If I turn the gain up, we're going to watch the edge shift to the left, so my sound path is going to get even lower, right? 1.011. And if I measured first peak, it's going to be somewhere kind of in the neighborhood of this as well, right? So first peak would be here, edge would be here. These are a lot closer than the max peak measurement was. Max peak was reading over. That's because the maximum peak is located further to the right, right? Further this way is going to have a greater sound path reading. So let's say that I wanted to do the acoustic wedge verification. I'm actually going to start with a new setup file, and I'm going to pull this probe off the cow block. And again, I've just got the probe off the cow block, and I'm just going to set it there. We're going to use this bottom surface of the wedge as a reflecting surface, and I'm going to walk through a simple setup. Tab 1 doesn't matter. Tab 2, I'm going to pick the probe, A1, 5L16 A1. I'm going to keep the wedge on contact. So again, I'm going to keep the wedge on contact here. The reason being, we're going to use the bottom surface of this wedge as a reflecting surface. We're actually going to map this out ultrasonically. So clean couplet, I'm not putting it on a part, and I'm going to tell the instrument contact, just like I did earlier with the 0 degree. Contact. Then I'm going to go to tab 3. And just like I did on the 0 degree, I'm actually going to pick a 0 degree with overlap. I'm going to fire one element at a time. And through beam spread in the wedge, we're actually going to map out the bottom surface, the ID surface of this wedge. So element quantity 1, just like if you're doing an element check. 0 degrees, longitudinal wave, that's what we want. Okay, and I'm going to get a signal like this. So what we've got is a couple little staircase patterns here, right? This first staircase is going to be longitudinal waves mapping out the ID surface of the wedge through beam spread. And then this second signal is going to be basically your second back wall. I've got to make some adjustments here. So I'm going to change my velocity to Rexolite, about 0.092. By introducing a different velocity, I need to go back and readjust the range so I can see what I want, and trying to zoom it in just a little bit more, maybe something like that. I'm going to bring this voltage down just in case I find later that it's too powerful. And I'm going to hop down to this points quantity. And again, man, I'm giving it a good high points quantity. That way I get better precision on my measurements. And so with that being done, maybe a little adjustment to that range. Let's see, I'll try to bump it down just a little bit more. There we go. That looks good enough to me. So one more time, I'm going to go to the gate screen, and I'm going to turn off gate I. I'm only going to use gate B, or gate A, the red one. That's all I'm interested in. And we know that this gate by default is set to read max peak. So what you want to do is just make sure that the gate is able to see this entire stack of wedge backwall signals, and you don't want it stretched out too high. So with max peak, it doesn't really matter what my amplitude is, and I don't really need to go back and adjust my gain, because as we've already established, it's going to read the maximum peak no matter what. So the things that we're going to be measuring here are this. I'm going to measure H1, which is the height of the first element. And what I'm looking for is this sound path reading. Actually, I need to grab one on the screen, so bear with me. I'm going to go back and just pick... Okay, good enough. I was wanting to make sure that my TA reading was reading correctly, and it is. So 208. So basically what I'm saying is, based on the Rexolite velocity, I'm measuring 0.208 to this VPA1, aka element 1, back wall. It's 208. So I'm going to record this measurement, 0.208. And that's something that we're going to call H1. I'll show you that in a few minutes. I'm going to do the same thing for this last element back wall. We're going to call this H2, so I'm getting a 0.432. I'm going to record those measurements, and I'm going to use those later. And remember, we are using maximum peak for this. Okay, so I recorded a few measurements a moment ago, H2 and H1. So as you can see here, H2 was the sound path, or the wedge thickness, for the very last element. H1 is going to be the height of the first element. And I've got a formula. So sine of the wedge angle, which I'm going to solve for this at the end of this, equals H2 minus H1 divided by total number of elements minus 1 times pitch. So let's look at what's going on in this formula. I arrived at a new H1 via this process, this is going to replace the wedge delay calibration, because that's all that the wedge delay calibrates. And then at the end of this, I'm going to be calibrating the wedge angle. So if the wedge angle and the velocity are correct, then the refracted angles have to be correct. So this is also taking the place of verifying your refracted angles, or verifying your angles, period. So this formula is going to be super handy. And I'm going to plug in those numbers that I got a few minutes ago for my wedge. I had 208 for my H1, and I had 432 for my H2. Okay, so what I've got here is a spreadsheet that has the acoustic wedge verification formula on it. This is something that I made several years ago, and I'll show it to people in my classes when I teach this. But basically what it's going to do, I'm going to input some values. It's going to calculate the wedge angle, and then I've also got a Snell's law formula in here so it can calculate Snell's law. So let's type in my values. I had 0.208 for H1 on that 5L16 wedge a minute ago. That was the height of the first element. The height of the last element, H2, was 0.432. And I'm using a 16 element aperture. So what this calculates for me is H1, the height of the first element, so that takes the place of a wedge delay, and it calculates my wedge angle, and then if I use Snell's law, it calculates my actual refracted angle. So this takes the place of a refracted angle verification. And this works great for curved wedges and flat wedges and all of them. So these are the numbers that I came up with. So we'll remember 208, and we'll remember this wedge angle. We're going to make a custom wedge, and then we're going to go back and measure this radius. Okay, so I'm going to go through, and I'm going to go to Probe and Wedge Manager, my wedges, and I'm going to pick new from. That lets me modify an existing factory wedge. And so what I was using was my SA1 N60S 5L16. I'm going to select that one, and I'm going to modify some parameters. So H1 factory default was 201, but I measured it with a highest peak gate to be 0.208. Okay, 0.208. The factory default wedge angle, in order to get a 60-degree shear wave, is 39, but I measured it to be 39.2 degrees. Okay, I'm going to make a custom file, so I'm going to call this, I measured it with peak, and I'll put today's date. And I'm going to save those changes. So all I did was adjust H1 and the wedge angle. I'm going to hit done. And now I'm going to go back to that 5L16 setup that I was using earlier. And instead of the factory wedge, I'm going to select this wedge that I just measured acoustically. And we're going to see how it works. I'm going to check edge and peak measurements, and then I might go back and tweak this wedge one time. We'll see what happens. So got the probe here on the cow block, and again, with that signal peaked, like we had earlier, we know that peak was reading a greater sound path because it's way over here to the highest peak. Let's see what happens when I select the wedge I just modified. So scan plan, probes and wedges. I'm going to pick user, 5L16 peak, slightly modified dimensions, not going to change anything else. And now I'm going to have to move my probe around to find the peak, right? I shifted my wedge delay, so I've got to move the probe just a little bit. Get it back, and I think it fell off, but right there, look at that, man. Oh, look, I need to move my gate back a little. Okay, let's find that peak one more time. Okay, so by doing the acoustic wedge verification, I mean, look at that. It could not get any more perfect than that. Literally exactly 1 inch, right? If I was using edge, though, then this is going to be reading shy of 1 inch. So if I just flip this to edge, right, now it's reading like 0.983. Or if I did first peak, it's also going to read low, right? So performing the acoustic wedge verification with the gate strategy, the way that you're going to test with it is how you're going to get best results. I'm going to prove that to you one more time. So I'm going to make a new setup, and I'm going to do this acoustic wedge verification in edge. And I just want to walk you back through the setup again. Tab 1, no changes. Tab 2, I'm going to pick the probe that I'm using, which is my A1 5L16. I'm leaving the wedge on contact. Later, I'll show you the wedge profiler. We're going to do this 0 degree with overlap with a 1 element quantity. 0 degrees, longitudinal wave, focusing doesn't matter. You can't focus with 1 element anyway. Going to clean off my wedge. And again, I've got to go through the setup. So I'm turning off gate I, it gets in my way, get rid of that. Turn on gate A. Going going to go to my UT settings and make sure that you put the velocity to equal the velocity of your wedge, so 0.092. And I'm just making some changes here to get it pretty much equal to what I did before. Back to my gates. And I want to start the gate just above this first signal. This is H1 right here, and I want to make sure the gate's not too wide. So I'm going to stop at, H2, the last element's right there. So I'm just encapsulating that area. And I'm going to start with VPA 1. That's element 1. And so the thing about using an edge gate like I'm about to do, amplitudes have to be consistent. Peak, the amplitudes don't matter, as I showed you earlier, but an edge gate, it really does. So I'm just going to get my signal at around 80%. And I'm using edge here. And I'm getting instead of a 208 like I got before with peak, I'm getting a 195 with edge for H1. And now I'm going to run over here to the last element. Amplitudes need to be consistent, so I'm putting it at auto 80. And I'm getting a 419 out there. And so even little things like your detection threshold of your gate, right? If my signal is at 80 and I measure it with a 20% gate, that's how I need to do my testing. Watch what happens with these measurements if I drop this detection threshold using edge. I'm going to drop it from 20 to 10. Let's see what happens to 419. See, it changed just a little bit, right? So you got to make sure you're consistent. And actually, let me remeasure these. So VPA 16 with a 10% detection threshold, I'm getting 417 for the last element height. First element, auto 80, now I'm getting 192. So I made some adjustments to my gate detection threshold. And if you do that with edge, you got to account for it. So we're going to remember those numbers. Okay, so now what we're going to do is enter in my new measurements from my edge gate. So H1, edge measured it at 192. H2, I got a measurement of 417. So that's now calculating, I got a 39.4 degree wedge angle. It was 39.3 a minute ago. And my refractive, so these numbers changed slightly. And I'm going to keep these in mind. I'm going to go make a custom wedge in edge, and we're going to see how well it did. Okay, so we're back on the OmniScan. I'm going to go into Probe and Wedge Manager, and I'm going to do just like I did before, new from SA1 N60S 5L16. And I'm going to type in the numbers that I measured with edge, so 192. And then my angle, I'm getting a 39.4 as opposed to the standard 39. Okay, I'm going to rename this one edge. Today's date. Save it. Done. And I'm going to go back and open my setup that I was using on the radius right there. And put the probe on the cow block. There's my nice radius signal. Okay. So we'll just leave that there for a minute because things will shift a little bit because I've got to select the other wedge. Right now, I think the factory wedge is still picked because I didn't save my setup file earlier, but I am going to go through now and I'm going to pick the edge version that I just made right here. Not going to change anything else on this screen, only the wedge. And let's see here. Also, I will be making an adjustment to the gates here in a second. But first off, let's just see. So if I peak up this signal from the 1-inch radius, my gate is still set to read max peak right now. So chances are it's not going to be very accurate, right? Let's put this gain at auto 80. So max peak is reading 1.023. I'm going to stretch this thing back a little bit, make sure it was at a 10%, okay? Max peak is reading 1.023, but I did my acoustic wedge measurement in edge a moment ago. So check that out. I change it over to edge, And again, just really be sure that I'm peaking up in the right spot. And it's much closer, right? My edge measurement, since I did the acoustic wedge verification in edge, and now I'm measuring with edge, then my sound path measurements are going to be much closer. If I were using peak to measure for my job, I would need to do peak for the acoustic wedge verification. That's just how it is. That's how you get the best accuracy. Okay, so the next step that I'm going to do, I'm going to verify the refracted angle, because this wedge verification is not just there for wedge path, it's also there for a refracted angle. So I just grabbed a mini IAW block off my shelf, and what I'm going to want to do here is first find the beam index point. And remember, this is my modified wedge. So I'm using my 60-degree angle, and I'm peaking up. And the reason I'm using my 60 is because this is an N60S. So I'm peaking up the signal from that radius, and I'm just going to take my pen and I'm going to place a mark. So we should know how that goes, right? I'm going to place a mark on the wedge directly above that 0 marker on the cow block. And then I'm going to flip the cow block to find the 60-degree measurement location, which is right here, right there. And I'm going to go back and forth looking at that big circle, that big hole, and find the spot where it peaks. So right there. And the notch, the mark that I put on my wedge is directly in line with the 60. So I know that I've got a refracted angle that's verified, and I've also got a wedge delay, a sound path measurement that was also verified, because when I peak this thing up on the radius, remember, let's look at what that sound path measurement gives me. This should be a 2-inch radius. And then, I mean, look, right there, it's a 2-inch radius, right? So the acoustic wedge verification handled the wedge delay, and it also handled the refracted angle verification. And it would have worked the same way if I would have used the peak one or the edge one, right? You just got to make sure whatever you're going to use for testing, you also use during the calibration process, the acoustic wedge verification process, in order to get the best results. If you use another detection mode, then your measurements are going to be off, you know, a half a wavelength, quarter wavelength. It depends on how many lobes there are between your peak and the edge or the first peak that you're using. It varies. Keep that in mind. Okay, so the next wedge that we're going to check with this acoustic wedge verification, I've got a SA10 N55S connected to my 5L16 A10 transducer. And so what I'm going to do is I'm going to do the old school angle verification first. And just regarding my setup, I've made a 40 to 70 sectorial shear wave. And so I'm using the 55-degree angle, which should be the nominal refracted angle with no beam steering, just purely refraction, so 55 degrees. And on my IAW block, I am basically finding my beam index point or my beam exit point. And I know you can't see it, it's not directly straight up and down, but I'm putting a mark on my wedge with my little skinny Sharpie to measure the beam exit point. Now I'm going to flip the cow block around. And now I'm aiming my probe at the 2-inch circle on the IAW block in order to verify the refracted angle. So there's the signal for that. And I'm just going to move it around until I find the peak there, right about that position. Looks pretty good to me. And though you can't see it, on this cow block, my mark is lining up with about the 51. It's right in between 51 and 52 degrees. So this wedge has front wear, which means the angles will be a little bit lower than anticipated. So my N55 is measuring to be about a 51 or 52 degree. So now we're going to do the acoustic wedge verification the manual way, and we're going to see if that holds up. And then eventually we'll fix and make a custom wedge, and then we'll put it back on the cow block and see our results. Okay, so I'm making a new setup file with this probe and wedge, and what I'm going to do is go through and set it up for the acoustic wedge verification. So the material doesn't matter. I'm going to pick the transducer. So this is actually a A10P. It's a plastic case. I'm going to keep the wedge information on contact, and the setup I'm going to build, we'll do a linear at 0. The big deal here is linear, L wave, 1 element quantity. Focusing doesn't matter, but you want it to be a 0 degree angle. And then I'm going to get my staircase pattern here. I'm going to turn off gate I. Again, it just kind of gets in my way sometimes. So back to gate A. And then under UT settings, we've got to input the velocity of this wedge. So this is Rexolite. It's about 0.092 inches per microsecond. Since I introduced a new velocity, I'll have to adjust the range just a little bit as well. And I'm going to go through, and I'm measuring this in highest peak because that's how I'm going to measure it on the cow block itself. So we're going to go through, and I'm also going to add a pretty good points quantity here. I want to get a really good high resolution A scan on this. And again, I might bring that range down just a hair to make it a little bit easier to see. So all that looks pretty good. And my gate mode, I'm just using highest peak, max peak, because that's what I'm going to use to test with. So what I'll do is VPA number 1, we're going to call that H1, and I'm going to record a sound path. I actually need to set up a sound path reading. So let me get that real quick, and we'll do. Okay. And I always like to do that just to make sure that that TA reading is giving me what I want. So I'm going to write this down. So I'm getting a 247. We're going to call that H1. That's going to be the height of the first element. And then I'm going to go down to the last element. And since I'm in peak, it's not necessary to do an auto 80, but I just prefer to. The last element height is going to be 0.447, and we're going to call that H2. Okay, next, I'm just going to add those numbers into my spreadsheet for calculating the wedge angle, and now we're going to see what we come up with. Okay, so I'm going to input that information here. So when I measured the wedge a moment ago, H1 I measured at 0.247. H2 I measured at 0.447 inches. The pitch on this one is a 0.6 millimeter pitch, and I've got 16 elements. Okay, so this is what I calculated. And if you remember, on the cow block, I said that the wedge angle was showing up between about 51 or 52 degrees. So look at that. Snell's law has calculated that the refracted angle is 51.75. That makes complete sense, right? And, you know, the nominal refracted angle of this wedge should be 36 degrees, 36.1 degrees, and I've calculated it at 34.3. So since this wedge has front wear, the angles are lower than anticipated, and this lines up exactly with what I saw on my cow block. So now what I'm going to do, I'm going to tweak the factory wedge definition. So I'm going to go into main menu, probe and wedge manager, my wedges, and I'm going to hit this button down on the bottom, new from. And what I'm looking for is the factory wedge definition here. So I'm going to go down to SA10, N55S, 5L16 right there. And so what that's going to allow me to do is I'm going to edit the factory parameters with the new ones that I just measured. So the first element height that I measured a moment ago was 0.247. You can see factory, it was 274, but this wedge has been worn out. So I'm going to do a 0.247 here for the first element height. And then the wedge angle factory was supposed to be 36.1, but I calculated like 34.36. So 34.36, and I'll just let the machine, I'll let the OmniScan round that number. It'll be, 34.4. So what I've done, I've added the first element height that I've measured acoustically. I've added the wedge angle that I've measured acoustically. I'm going to rename this wedge so I can find it here in a minute. So I'm just going to call this peak. And then today's date, it's February 1st now. Okay, so this is my custom wedge with my modified parameters. I'm not going to change anything else. Now, you know, to get the most accuracy possible, I could take a pair of calipers, right? And I could measure, you know, any of these things to make sure nothing has changed. But let's just see what we come up with me just modifying first element height and wedge angle. So I'm going to save changes and I'm going to hit done. And that's it for the acoustic wedge verification and the custom wedge. Now I'm going to go back and open my setup that I was using a few minutes ago. It was a 40 to 70 degree shear wave sectorial. Okay, so the change that I need to make here on my setup, I'm going to pick that custom wedge that I just created. So this is the factory wedge, but I'm going to go down here to user and I'm going to pick the one that I just tweaked a moment ago. That's going to be the one that I use for my focal law check. So a little bit of coupling on the IAW block, and let me zoom out and then zoom back in here. So I'm using my 55 degree law. That's the one, that's the nominal refracted angle of the wedge. That's the one that I'm most interested in at this point. You know, in actuality, you'd want to check several focal laws, but I'm just kind of focusing on the nominal refracted angle of the wedge at the moment. And find the spot where the signal peaks, and I feel like it's right there in the middle of that little A-frame that I drew on my envelope. And I'm going to get my Sharpie, and I'm going to measure, I'm going to mark that beam exit point. It's pretty much in the same spot that it was before, honestly. But now this is going to be the telltale here to verify the refracted angle. Earlier I was measuring about 51 or 52 degrees, but now we're going to see where it falls since I've modified that wedge. Okay, now to verify the refracted angle, I'm aiming my probe at the 2-inch circle, and I'm finding the spot where this signal peaks, and it's going to be right about there, right about there. And my mark is now at, you can't see it, but it's right between 54 and 55 degrees. It's much closer than what it was. I'm not getting it exactly at 55, but I'm right there. I'm between 54 and 55 degrees on my IAW block. I wish you could see it, but it works. After doing the acoustic wedge verification, it worked. And also something I didn't check a minute ago. Let's just see how my sound path looks. So obviously the refracted angle showed up correctly. Let's look at my sound path on the radius to see if basically my wedge delay was also taken care of. So I'm looking for the spot where this radius peaks. This is a 4-inch radius right there. And let's see, what was my sound path there? I'm at 3.996 inches. Supposed to be 4 inches. I would take that, you know, just moving my probe changes it a little bit, but you can see it's perfect, right? I mean, I'm right there at 4 inches. So the acoustic wedge verification took this wedge that was worn at an angle. It corrected the angle, so I got my 54, 55 degrees that I should have got out of this wedge. And also, so that took the place of verifying the refracted angle, right? And then it also adjusted my sound path, my wedge delay. So the acoustic wedge verification handled the wedge delay and the wedge angle verification on a wedge that was worn at an angle outside of our typical tolerances. So by doing this process, I'm able to extend the life of this wedge, because otherwise, if I didn't have a way of adjusting that, I would have to throw the wedge away because it was just outside of my 2-degree tolerance. But now we're good to go for a little bit longer. So that's how you do it. So I wanted to show a few examples of some wedges that I had measured over the years, and I've got some really good images of these and some really good data. So this first one, this was a SA10 N55S wedge. Had, you know, a little bit of wear, but very minor, not enough to really throw off anything. There's a chart on the bottom that's got the nominal H1, the nominal wedge angle, and the nominal refracted angle values. Those are in yellow. And then you can see over to the left, let me look over here for a sec. So nominal H1 was 274, I got 271. Nominal wedge angle was 36.1, I got 36.5. Refracted angle, 55, I calculated 56 with Snell's law. So these SA10 wedges, they gave you these really nice bevels here over on the side. And they were a really good telltale as to whether you had significant wear or not. So that one wasn't too bad. This one, okay, so nominal H1 was 274. I calculated 207. This had a significant amount of wear. But look, the nominal wedge angle is 36.1. I calculated 35.8. That's not too bad. There was significant wear on this one, but it was very level and even. This is the type of stuff that a traditional wedge delay could correct for here. This is what it was designed to fix. Not angle, just level wedge wear. And the nominal refracted angle was 55. I calculated 54.79, so pretty good. You can see here that the wear was significant, but it was pretty level. Those tapers, that bevel, it's still pretty level. So let's look at another one. Okay, this one was on one of my chain scanners, and it had made, hundreds, if not thousands of passes around a pipe. And literally this wedge was being used that day. I pulled it off just to do this test. You can see these grooves that run from side to side on the wedge. That wedge has been spinning around and around and around a bunch of pipes. You'll notice that the wear here is fluted more towards the front, right? Can you see that? It's kind of tapering out or flaring out towards the front. What that means is the wedge angles are going to be lower than anticipated. So down here, I've got the nominal H1, calculated H1. I've got the nominal wedge angle, 36.1. I calculated that. I measured it with the acoustic wedge verification to be 32.5, so way lower. And this 55-degree wedge was actually 48-degree wedge, right? So significant front wear. A wedge delay would never have fixed this, a traditional wedge delay. With an acoustic wedge verification, I could fix this. I could arrive at the proper parameters, and I could make those into a custom wedge, and I could keep using this. The only thing is those grooves would have given me a really nasty looking signal at the surface, but I could have at least fixed for the geometry. Chances are, if you have a wedge that looks like this, you should probably just throw it away. Okay, this very last one is going to have significant wear towards the rear. So my buddy, this was again a wedge out of my group. My friend that I used to work with, he put a lot of back pressure on his probe. So you can see very smooth wear, right? There's no grooving like what we had on the previous one. This was a manual scanning probe, and he put more pressure towards the back. So you can see that these bevels have tapered more towards the back. If the wear favors the rear, you're going to have higher angles than expected. So you can see down here, we've got the nominal H1 and the calculated H1. We've got the nominal wedge angle. It was supposed to be 36.1. Calculated it to be 40. And after running Snell's law, this is an N64 wedge now, not an N55. So again, these were a few examples of some wedges that I pulled out of service that day when I decided to do this project. I guarantee that you and your group, you probably have wedges that look like this too. So your two choices are either fix it with an acoustic wedge verification or throw them away, right? Or keep using them. But if you keep using them, you're going to have really bad results. That's why we're doing this whole discussion in the first place. Okay, so I'm going to let that be it for this video. I know this took a little bit longer than I would normally want to, but there's a lot of things to point out here with the acoustic wedge verification. I teach this process way more in depth in my classes, my phased array classes, my TFM class. Check out the video that Olympus put out, Chris Magruder 10 years ago, improved calibrations for better time of flight measurements. I'll leave a link down there below the description on this one down here. Check that out. It'll walk you through it a little bit more. It would take a while, but you saw me go through the steps a few times. The biggest thing I wanted to drive home is the gate detection strategy matters. If you're going to use peak in your inspection, do the acoustic wedge verification with peak. If you're using edge, use edge. First peak, right? So take care, and I'll catch up with you real soon.